Hello and welcome to this video on the introduction of computer science. Here in this particular video, we will be going over the generalities of what's included in computer science. As far as this particular playlist goes, this will go into general topics and rants, arguments included within the realm of CS, not necessarily included to programming or any particular game design, whatever topic. So without further ado, let's continue on with the slideshow. So what is this channel about, Solid State Society? Basically, you can learn computer science completely free. Here you can learn about general concepts, ideas, and executions for computer science, henceforth referred to as CS, for basic definitions, coding, and documentation. So who am I? My name's Marin. I do game design, XR, UI, UX. I do everything, but this is what I like in particular. So I enjoy programming for game design. I dabble UI, UX stuff for fun. I really enjoy programming when it involves some kind of interactivity because, well, it's easier to debug for one, but there's some kind of back and forth between like the user and whatever the program is, so I really enjoy that. And yes, it's also because it's easier. And I also really enjoy playing with hardware and checking out what the interaction between like software and hardware is. For example, like Arduinos, they're really easy to learn about. Maybe I'll make some videos on that, but other than that, let's continue on with the video itself. So what is computer science? Just as is, right? The idea of computer science is everything from the study of computers, starting from like the theory, the hardware, the software, and the methods of implementation. So we'll consider these as 4 different realms, and I will go into what is included for each one. So let's go with the first one, starting from the top, theory, in terms of discipline, right? So with theory, right, it's a really abstract and mathematical representation of how to best and most efficiently solve problems given some solution that you find, right? So flat out, this is the most mathy that CS will get. When I first started learning programming, I was actually told by my instructor, you don't have to be a mathematician, it helps, but you don't have to be. This is where, if you're a math person and you enjoy that, this is your best area to go into. In terms of what you'll be doing, let's go into that. So one area is data structures and algorithms. So this is just talking about things such as optimization in terms of how fast it can be, space. But as far as a definition goes, I feel like that's all repetitive. So it's a commonly used method for computation and how effective it's going to be. There is a difference between data structures and algorithms, and those differences are: data structures, or just structures, are a method of organizing and managing data in such a way that it allows it to be modifiable. In other words, you have some generalized thing wherein you can reuse it for whatever suits your specific needs. An algorithm is a finite number of steps and instructions given to solve some given problem. So where it differs from, say, a structure is that the algorithm is the implementation itself, and this goes into, again, the overall like optimizations, or I don't know, just how to do something, right? It's the implementation. The next thing we can go on to is the theory of programming, and this is how efficiently a problem can be solved using a basic model algorithm. Theory of programming also gets into the different languages, and there's a lot, and like within the 1,000, maybe more. There's new ones that come out like every day. Information theory is how to quantify, store, or communicate information. This is a little more than, say, databases, which we'll get into later. Information theory is just how to actually work with information itself. It's like a higher level than just like a database. This is also kind of mathy, but one of the less mathy ones within theory. Coding theory, the properties of code and how much it will fit that specific need. So number of things that we can go into for coding theory. Data compression, which is also known as source. This takes the source data, makes it smaller. Very important in this day and age. Error control, or also known as channel. This will detect any errors, show any potential fixes. This is where compiling will come in. cryptographic, secures information, communication, sorry, and line, which is like the code chosen for communication. And this is like really low level stuff. I mean, like, when you get into, say, something like, I don't know, like line, right? This is like what you're choosing to, say, encrypt your code with, or something, or some line of communication which you're going to choose. And we have programming language theory. As I mentioned before, there's like a bajillion languages. New ones are made every day. So programming language theory is designing, implementing, individualizing, classifying, and analyzing the differences between languages. We'll get more into this when I go into the introduction to programming, particularly in C++. Long story short, I love C++. I think it's a really good language to learn. Even though it's a little older and technically a little harder, it's a great introduction to the different areas of programming. It's object-oriented, so on and so forth, but we'll get to that when we get to that. Formal method. This specifies how to implement any given system, as well as how to verify hardware or software. So different areas to study within each different discipline of theory, right? So for data structures and algorithms, there's just making algorithms, there's analyzing them, which is, for time, just to check how fast it is, that's big O, and I guess big S would be space complexity. Excuse me. There's data structures, there's combinatorial and like optimization, and then there's computational geometry. In terms of theory of programming, there's automata theory, there's computability theory, complexity theory, cryptography, and quantum computing. In information theory, there's lossy-lossless compression, channel coding. In coding theory, there's source coding, channel coding, line coding, and cryptography, and then data storage. In programming language theory, there's type theory, compiler design, and just designing your own language. And in formal method, there's logical calculus, automata theory again, and program semantics, type systems. Obviously, this isn't inclusive, but this is like a really, really generalized thing of different areas you can go into for studying. Now, in terms of different jobs in the discipline, there's like, you could just be a professor, you could be a consultant, algorithm analyst, compiler designer, intelligent assessment, and like a cryptographer. Again, very small niche things, and this is just a basis of different jobs you can get. It is not wholly inclusive. That would take forever to write. Next area which you can go into, computer systems. This discipline is just hardware. Doesn't have to be exclusively hardware, but it's hardware if you want to generalize it. And now, a computer system is defined as a basic, complete, and functional computer with all the necessary hardware and software needed to be considered functional. So, if this was a computer organization and architecture class, I would go into more what makes a computer whole, but this is just really general. So let's go into the different areas. So there's computer architecture, and this is the set of rules and methods that describe the organization, functionality, and implementation of the whole system. We go on to computer performance analysis, again, really mathy. This is the analysis of the workflow of a given computer and how to control certain areas to make the computer most efficient. So maybe a little more than algorithms, this goes into the hardware as well. Networks, set of computers, or nodes rather, connected together to share resources. Now, if you recognize nodes, there's a couple different terms for nodes in computer science. This is just the hardware, the system itself. There's node programming stuff, but we're not going to get into that. This particular video isn't about programming. There's parallel and distributed systems, and that is the multiple computations can be executed simultaneously. And if this is an architecture class, we can go really into the differences, but all that you might want to realize for the differences right now is parallel is pretty much a bunch of different processors that have direct access to some shared memory, and distributed is independent computers that are interconnected, but they can work on their own. So cybersecurity and cryptology, we're just going to throw them together because they kind of have a lot of the same goals, but not necessarily the same implementation and whatnot, but together they protect computer systems from adversarial attacks. So security protects the information from unauthorized access, insertion, deletion, modification, and you have to maintain usability for the intended users while you're trying to protect them. Cryptology just secures the communication by encrypting and decrypting. Cryptology is really fun. I don't necessarily go into it in terms of like writing the code, but I really enjoy doing like deciphering on my own time. If you could understand that and you're decent with coding, the translation is not terrible at all. So databases. This is kind of just thrown under hardware because a lot of it has to do with how you physically store it as well, but databases are pretty much made for managing, organizing, and storing data. So areas to study within these disciplines are within computer architecture, there's digital logic, which means like the actual circuit boards, microarchitecture, multiprocessing, ubiquitous computing, systems architecture, and operating systems. Because I already mentioned what a compiler, and like now that we brought up operating systems, one thing to note is like if you're taking courses in those, compilers will make you a better programmer, but operating systems will give you a better idea between the interaction of hardware and software. I know this isn't programming, I just want to throw my 2 cents on that. Computer performance analysis, you can go into stuff like availability, response time, latency, processing and channel speed, bandwidth, throughput, and scalability. In terms of network, there is the Internet of Things, which is interactions between like just any old given object and something connected online. Like, you know those like fridges, like the smart fridges that cloud systems, cybersecurity, environment sensor networks, data integrity, and topography. This is a networking class, so topography is all those nodes and the best ways to connect them. In terms of parallel and distributed systems, there's scalability, system architectures, failure resistance, accessibility to memory, and threading. Threading is an advanced programming topic. We're not going to get into that, but it has to do with processors. So cybersecurity and cryptography, there's data loss prevention, penetration testing, forensic analysis, verification, data integrity again, and intermediaries. And in database, there's metadata management, data analysis, data and physical storage, visualization, data integrity for a third time, and verification. So just a quick thing about metadata. I know I keep going back to programming, but when you're dealing with something like, I don't know, you're writing in like an IDE or some kind of engine, whatever, right? You want to clear out as much metadata as you can because a lot of information is just kind of useless when you export it, right? You don't necessarily need all that background junk. But in something like databases, metadata could be important because, so getting into just a quick thing on databases, there's a very important difference between just any old given information and actual data. Information can be like whatever, but data is something that you can actually manipulate. So if I were to just give you a number like 6, that's information, but like what does it mean? So nothing is data until you have some kind of value attached to it. Maybe I say 6 meters, 6 acorns, anything, right? I've given it some kind of value, like manipulatable value. But yeah, so it can be really important for databases to have some kind of, I don't want to say metadata access, but you know, just keep an eye on it. Anyway, moving on. Jobs in the discipline will include computer engineering. That is not necessarily just hardware. You might have to deal with some software stuff, but you're also going to be working at a lower level. Electrical engineer, database administrator, data analysis, system analyst, and network administrator. Now we go on to computer applications for the next area, right? And this is, if you want to whittle it down, you could just say it's software. It's basically applications designed for some kind of end user. So we can go into computer graphics, which is methods for synthesizing and manipulating image data and content. You can do this for both 2D and 3D. Again, this is a really mathy area. If I were to look at pretty much anything else within the realms of computer applications, this is definitely the most mathy because manipulating data a lot of the time people think in 3D, right? So we have to think on like, if it's 2D, it's an XY axis, and 3D, it's like an XYZ, and there's a lot of manipulation going on. It's interesting though. Human-computer interaction, and then there's the reverse computer-human interaction. There is a difference, but we're just gonna throw it into here. And this is designing, implementing, and using technologies that best satisfies a user's experience, and it focuses on interfaces most of the time, but interfaces can be really broad. So, for example, obviously, when you think of some kind of interface, you're thinking of maybe like a GUI, whatever you're seeing on screen. But it could also be your mouse and your computer, your keyboard and your computer. I mean, you could just make your own controller, right? I don't know. They have the makey-makeys, and so long as it has some kind of current going on, you just clip that. I don't know. Maybe you clip it to like a dog's fur, and you just pet the dog, and that's a controller. Yeah, no, that's real. Look it up. It's great. So scientific computing or computational, this is really, really broad. So the way you want to think about it, if you're going to generalize it, is constructing mathematical models and quantitative analysis using computers to solve scientific questions, usually by simulations or using informatics. So if you really want to simplify this, it's about math models and simulations, and I guess informatics. If we were to go on, AI. Artificial intelligence is about synthesizing goal-oriented processes using either a defined set of instructions or some kind of information. So this will include something like machine learning. Just flat out, computers are really dumb. I mean, like, really dumb. So if you want anything to happen, you have to basically give it information almost exactly. Now, if we were to go into, say, other languages, right? Some things can be kind of like you give them the goal and it can infer how to go about it, which I guess if you want to relate to AI can be considered like machine learning. You just keep feeding it info and it'll figure something out if you wrote it well, or just write really detailed instructions so that you can say, I don't know if you're making like a robot. Okay, this is what a wall is. If you were to hit it, just make a slight turn. If you're, I don't know, stuck in a ditch, spin your wheels a lot and try to keep pushing upwards. Not really the best situation if your little robot's stuck in a ditch, but it's something, right? So if we were to go into the areas of study, there's like computer graphics, there's image processing, visualization, computer vision. Computer vision is basically the machine learning math part for computer graphics, where you're just feeding a lot of info and it'll try to figure out maybe some kind of points in an image. Rendering, animation, and geometry. Human-computer interaction, there is user interface and customization, extended reality or cross-reality, XR, social computing and entertainment. Scientific computing has numerical analysis, bioinformatics, computational physics and chemistry, and math modeling. AI has stuff like robotics, machine learning, computer vision again, data mining, pattern recognition, and natural language processing. All really, really cool areas. And some of the jobs that you can get are software developer, game developer, animator, more on like, I'll say, the CS side. So you might be dealing with how exactly are we going to model cloth simulation and how it'll react to anything in the environment, like wind, right? Not that like art side animators don't deal with that, but you're going to be dealing with the actual creation of that. VFX designer, data science, big data architect, and machine learning engineers. And last but not least, in terms of the areas to study, there is software engineering. This is just programming, implementation. So this is designing, implementing, modifying, and troubleshooting of software in order to have a finished product. Doesn't mean you're not going to be interacting with hardware, but if we're going to like simplify this, we can just say that it's like just software. So different things that we can do in terms of software engineering is, everything described above. And I know I just went on to the next page, but some of the presentations designs that we used here. Thank you guys very much. I hope this was a decent introduction into CS just in general. Again, this playlist will be for overall rants or just discussions I think are important for CS or any given topic within CS. You can find me at any of these sites below, and feel free to leave a comment. I'll do what I can to read it. Thank you guys very much. I will see you all next video.